So today we're going to look at the pressure and volume relationship for gases, and then we know this is Boyle's law. So Robert Boyle was looking at how changing the volume will affect the pressure of a gas. And in this whole part of the course, the laws we're dealing with will be dealing with pressure, volume, and temperature, and how those things are interacting with each other. So before we get too deep into Boyle's law, let's just talk a bit about gases. So we've seen we use gases all the time to like as a cushioning effect, like airbags, air mattresses, suspension components, so like there's gas shocks, things like that. And it's because gases are compressible. And we understand that the reason why gases are compressible is because there's lots of space between the particles, so we can actually push them back together. But at one point, they didn't really understand that part. They didn't really think of the kinetic and molecular theory and the spaces between particles. They were trying to figure out what's causing this, and what is that relationship. So Robert Boyle was actually researching what they called the spring of air. And they at one point even thought that if you had an air molecule, let's just say that's an air molecule, or sorry, a molecule, and it's in the liquid phase, when it turns to gas, it actually will coil up and make kind of this spring shape. So the molecular structure changes to give it that springiness. It's not necessarily about density and compressibility, it's about the shape of the particles. We now know that that's not true, it's just the molecules move faster and they spread out more. But that's what Robert Boyle was trying to figure out. He's trying to look at the spring of air and how pressure and volume were related to each other. So what he did was he trapped a fixed amount of air into a J tube, and then he used mercury on the other side to trap that airspace. And by adding or removing mercury, he could change the pressure on that trapped amount of air. So the amount of air was kind of stuck in there. It was constant. He doesn't have to manipulate it with hands or anything like that, so the temperature's constant. But he can change the pressure and see how it affects the volume of that gas in the airspace. And so that's what he basically did. So you have gas trapped in here. This is a sealed end of the tube. And there's atmospheric pressure there, and you can pour more mercury in here and add more pressure. So if you added 760, you've added another atmosphere of pressure. In this case, he would have actually doubled the pressure from the original pressure of the atmosphere to double the pressure of the atmosphere by adding an extra 760. So the key here is he's changing the pressure, measuring the volume, seeing what happens, and he's holding two things constant, the amount of gas and the temperature, because both of these would affect the pressure and or the volume. But we want to see just how volume and pressure are relating to each other, so we need to hold everything else constant. So temperature must be constant, the amount of gas that he's trapped must stay constant, he can't have any leaks or anything like that. Otherwise the results wouldn't show us how just pressure affects volume. So that brings us to Boyle's law. And he noticed that as he increased the pressure, the volume decreased. Kind of makes sense. You push on something, it squeezes, it gets smaller. We call this an inverse relationship. So as one variable goes up, the other variable goes down. Lots of inverse relationships in the world. The older I get, the less hair I have. That's what makes it inverse. If something's direct, that means that both variables will go up or down together, where inverse one goes up, one goes down. So Boyle tried to find a mathematical relationship for this, and in order to do so, he did his experiment, measured a bunch of volumes at different pressures, and collected those results. Now, if you're looking for an inverse relationship, what you'll find in math is if you take, for example, let's use our two variables, pressure, and you times it by volume, you'll get a constant value. If it's a direct relationship, if you went pressure over volume, you would get a constant value. So if it's direct and you divide, you get a constant. If it's inverse, you would multiply and you get a constant. I'll show you what that means in a second. So what we're going to do is we're going to switch gears. We're going to go to a simulation, a lot like what we do in class with the syringes and the pressure sensors, but it's just an online version of it. And I've got a syringe here, and I've got a pressure sensor, and we've got some air trapped in there. So there's 30 mils of air. And I'm going to move this piston around, and we're going to get a bunch of volumes and pressures. So in the notes, there's space for 4, so let's pick up 4. So I'm going to move it to 5 mils, roughly, get a pressure. Let's move it down like 12-ish, sure. Let's go like 20-something, and let's go there, 28. So if I take these data points, we can actually draw a graph, and what you see is this curve that's kind of going down, but in a curving shape, not a linear shape, and that's indicative of an inverse relationship. If we take these values that we have here and we're going to multiply them, like I said earlier, if we times volume by pressure, we get constant if it's inverse. If it was direct, we'd have to divide. So let's see what happens when we multiply these two variables. So we get 5.16 times 29.07, and that's 150. If I take 12.63 times 11.88, I get 150. If I take 21.15 times 7.09, I get 149.95, which rounds up to 150. And 28.41 times 5.28, and I get 150. So we can see already that when we multiply these values, we get constant values. So in chemistry, we often call that constant a K. K representing the word constant. C is used for all sorts of things. So I'm going to transfer back to the notes here, and we're going to enter the data points in here. So we multiplied the pressure and the volume, so P times V, and we got a constant value of 150 for all 4 trials, give or take a little bit based on rounding. So now we go to the next bit. What do we notice about the values? Well, they are the same. Is there a difference between the results? Not really. And is it significant? I would say no. If we did this lab in class, which we will, you'll notice that your constant values will not be all that constant because there's lots of error in the lab, and we'll talk about sources of error, but for this simulation, it's pretty darn close. Based on our results, state in words what you think Boyle's law may be. So I'm going to say that if we take the pressure times the volume is constant. So we're going to put it as a formula. P times V equals K, K representing a constant. So that is Boyle's law, basically. And here it is. If the temperature remains constant, the product of your pressure and volume of a gas has a constant value. So the formula for this statement is that P times V is K. And I just put K1 there just for a second. Just bear with me. So P is the pressure. We can have the pressure in any unit, atmospheres, millimeters, mercury, kilopascals, millibars. V is the volume. We can measure that in liters, centimeters cubed, whatever. It doesn't really matter what the values are. And then K is just some sort of constant, just like that 150. That's just a constant number that always multiplies to that number. So this allows us to figure out, if we know one pressure and volume, we can figure out what volume and or pressure we would have at any other volume and or pressure. So if we have 2 trials, if we know pressure 1 and volume 1, we can find what pressure 2 and volume 2 would be using this idea. So since we know that if we took P1 and V1, we would get K1. If we take P2 and multiply it by V2, notice we don't get K2 because it's a constant. It's the same constant. So we still get K1. So if this is equal to K1 and this is equal to K1, then what we can say is, well, they're both equal to K1, so they're both equal to each other. And this would be a way to work with Boyle's law. So if you want to know this or use this as a formula, this is an easy way to do it. There's Boyle's law. So if you know one pressure and volume, you can find another pressure and volume. So note, we have to have the same units. So if you've got, let's say, this pressure in atmospheres, this pressure has to be in atmospheres. If this volume's in liters, this volume has to be in liters. It doesn't matter which units you choose as long as they are the same. Okay? We can't have one volume in liters and another volume in quarts. It's just not going to work. We need to be all talking about the same units. So make sure we convert our units if we have to. So here's some example problems. We'll go through. I know I've got 2 methods in which I do this. So the first method, I'm going to call it the formula method, and that's kind of the old physics plug-and-play way. We'll call this formula method. So what we do is we go through the question, and we read what we have, and we set up our formula, and we write down our unknowns and knowns, and we solve, just plug the numbers in and solve. So it says a gas is in this container at a pressure of 608. So we have this volume at this pressure. And then we increase the volume to this. So this is the new volume. So I'm going to call this V1 and P1, and this is V2. We want to know P2 is question mark. So that's what I'm going to put. So our formula is P1 V1 equals P2 V2, right? And we now know those volumes and pressures. So P1 is 608 millimeters of mercury. We should be writing units beside any number that we write because they are measurements. And V1 is 545 centimeters cubed. P2 we don't know, that's what we want to find, but V2 is a 1065 centimeters cubed. So to solve for P2, we need to divide both sides, I'll do this in red, by 1065 centimeters cubed. Right? We do the opposite operation to both sides. So P2 is going to equal 608 times 545 divided by 1065. So I'll punch that in my calculator. 608 times 545 divided by 1065. I get P2 is equal to 311.14, and then the units that are left, if you actually go back and we cancel everything out, centimeters cubed cancel, the units are mmHgs, which is what we're looking for. We're looking for a pressure. Now, I prefer using what I call the logic method. I'm going to call this logic, or ratio method. And basically what we're doing is we're going to set up a ratio to make the volume or pressure change the way it's supposed to change. So if we look at what's happening, we have the two volumes. So this volume goes from here to here. So the volume in this increases. So volume goes up. And because we know that this is an inverse relationship, we know that the pressure should go down then. If we're increasing the volume, we're decreasing the pressure. So what we're going to do is we're going to take the pressure we have, so 608 millimeters of mercury, and we're going to multiply by a ratio of the two volumes to make this number get smaller because we want a lower pressure. Pressure 2 should be lower. If we go back to this question, or to the original, the formula method, we know that the volume's going up, so the pressure should go down, and this is a way to check. Did our pressure go down? It was 608, now it's 311. So in this one, we're going to set this up to make 608 get smaller. So with these two volumes, I've got to make it get smaller. So I'm going to put the bigger volume on the bottom, so that's 1065 millimeters of mercury, and the smaller number, 545 centimeters cubed on the top. Or sorry, and this is not millimeters of mercury, this was centimeters cubed. My mistake. They're both volumes. So what ends up happening, you can see that the centimeters cubed cancel each other out, and we're going to take our 608 times 545 divided by 1065. It's the same math as what we have here. It's just, instead of writing out the whole formula and just doing this cookie cutter math thing, we're actually thinking about what the relationship is, setting up a ratio to make that happen. So by doing so, we're going to get the same answer of 311.14, and the answer is going to be in millimeters of mercury. So I set up the ratio to make that volume, or that pressure, go down. So we'll do another one. We volunteered to decorate the gym with 300 helium balloons for a dance. We can get a 25-liter tank at a pressure of 30 atmospheres. Every balloon is going to hold 2.5 liters at a pressure of 1 atmosphere, roughly. So we want to know how many liters of helium we'll have, because if we take this tank that's under high pressure and we release that helium is going to expand because the pressure is dropping. So let's set up our equation. We'll do formula method, then we'll do logic method. So we're dealing with pressure volume, so P1 V1 equals P2 V2. So the gas starts in our tank, so there's V1. And the pressure in the tank is 30, so that's P2. And outside the tank, the pressure, or sorry, this is P1. P1. And the pressure outside the tank is P2, what the pressure is becoming. So I'm going to set up my equation here. So I'm going to put my P1 is 30 atmospheres. V1 is 25 liters. And P2 is 1.04 atmospheres, and V2 is what we're trying to find. So we rearrange, we solve for V2. Again, we divide both sides by 1.04 atmospheres. 1.04 atmospheres. These cancel. So V2 is going to equal 30 times 25 divided by 1.04, 721.15 liters. Now, again, ask yourself, does that make sense? You have the gases compressed in this original tank. You open the valve. It's no longer under pressure, so it can expand. The volume gets much, much bigger from 25 liters to 721 liters. Now, the question didn't want to know what volume we would need. We want to know if we can fill up enough balloons. So every balloon takes 2.5 liters. So I'm going to times by one balloon by 2.5 liters, because every balloon is 2.5 liters. Look at liters cancel. So we can now figure out how many balloons we need. So we're going to take 721.15 divided by 2.5, and that is 288 balloons. So we won't be able to fill the 300 balloons needed. So no, one tank isn't enough. So now doing this logic method, it's the same idea. We're going to start with, we're starting with our volume because that's what we're trying to find. So I'm going to write down my volume, 25 liters. And I want to figure out what the new volume is going to be. So we know that the pressure is going down from 30 to 104. So that means the volume has to increase. So we're going to set up the ratio between atmospheres and atmospheres to make the volume get bigger. So that means that 30 has to go on top and 1.04 atmospheres has to go on the bottom. And notice it's the same math as this. So it ends up being the same answer, 721.15 liters. And then again, we're going to times by one balloon for 2.5 liters. So that gives us 288 balloons. So the answer again is still no. So take a second, give the next one a try, and then you can pause the video. I'll correct it in a second here, and you can check your answer against mine. So again, I'll do both methods. So the formula method, I know that I'm dealing with pressure and volume. So before I do anything, I noticed, just as I was going through that this pressure and this pressure are in different units. So I want those units to be the same. Now, I can convert them both to millimeters of mercury or to atmospheres. It doesn't matter which unit you use. But I'm going to work smarter, not harder, because I already know that 760 millimeters is the same as 1 atmospheres. So I don't even have to do a conversion there because I know that already, because that's what's equal. 1 atmosphere is 760. So I'm going to work in atmospheres just because A, the numbers are easier, and B, that's a quicker conversion. So I'm going to write my formula down, and this is how we should always do formula method. You always write your formula, P1, V1, P2, V2. We show our substitution, our work, and our answer. So I'm going to read through. So it starts at 25 and 1, and we're looking for new volume at the new pressure. So this will be my V1, this will be my P1. New volume is my V2, and this is going to be my P2. So I just take those numbers and put them in. 1 atmosphere times 25 liters equals P2 is 1.25 atmospheres, and V2 is what we're trying to find. So both sides, divide both sides by 1.25, so V2 ends up being 1 atmosphere times 25 liters divided by 1.25 atmospheres. So now we cancel out atmospheres. 1 times 25 is 25 divided by 1.25, and we get V2 is 19.53 liters. And if we're doing logic method, we're going to think about what our answer should be. So the pressure is gone up. Went from 1 atmosphere to 1.25. So that means the volume better go down. And my volume did go down from 25 to 19. So I probably did that right. Doing the logic method again, that's what we're going to say. The pressure is increasing, so the volume must be decreasing. So let's set up our volume to make it go down. 25 liters. I want to multiply by the ratio of the two pressures, but I want to make it get smaller. So I'm going to put the bigger pressure on the bottom and the smaller pressure on top. So it's the same math again, and you end up with 19.53 liters. It's the same calculations as the formula method. It's just a little quicker, and you're just stating your relationship, which is kind of why I like it, because this whole part is more about the relationships than just plugging numbers into an equation and solving. Okay, so we'll be doing a lot of practice with this in class, and then we'll move on to Charles' law and then Gay-Lussac's law.